How's it going, everyone? Mr. Geyser here with the second video in our Lesson 13A series, where we'll be taking a look at example 4, 5, 6, and 7, where we're taking it up a notch with using these logarithm and exponential properties. We can use the definition of logarithms to rewrite exponential equations in order to solve them. When solving logarithmic expressions, be sure to determine the domain of the variable first to avoid extraneous solutions. What I mean to say is, when we use these kind of properties here, we are going to create some extraneous solutions that we can't plug in to our original problem here. We need to use some double checks to make sure we're not plugging in negative values into our logs here. And we want to make sure that we're plugging in only positive values that allow us to create some solution for these equations. Let's put this into practice first. We're given this log base 2 of 4x is equal to 5 here. And really, I want to try and manipulate this so I have the same log base. But there's no real way for me to try and create a log base out of nothing on that right-hand side. However, I do have the base of 2 here for log. And I know that if I raise to the power of 2 to both sides using that property of exponential property of equality, I can say that this whole left side here, raised to the power of 2, is equal to that whole right side there, raised to the power of 2. When I do this, look what happens to my log base 2 and my base 2 of my exponential function. They simplify out. And I end up getting the internals of that log that's left on my left-hand side. So I get 4x is equal to, well, 2 raised to the 5th power is just equal to 32. And now I have something that I can easily solve. I just divide both sides by 4, and I get x equals 8. In this case here, I get a single answer of x equals 8. So let me just double check that real quick. I'm just plugging that x equals 8 into my log base there, where I get log base 2 of 4 times 8 is equal to 5. But I don't have a good calculator that gives me a custom log there. So I just need to remember that I can just do log of 32 divided by log of 2, and that still gives me 5. Easy. Let's try that one more time with example 5 here. In example 5, we have log of x plus log of x plus 15 is equal to 2. I'm just going to rewrite that real quick. And first we need to deal with this left-hand side where we have these 2 logs here. And I want you guys to remember to those log properties where we can squish them together as long as we use a product between the internals of the log. What I mean to say is that log of x, that x is timesing that log of x plus 5. And we get this internal of log of x times x plus 15 is equal to 2. Now, all I need to do is raise to the power of 10 now, because that's a log base 10, a common log. And this log of 10 and that exponent, or that exponential function of 10, simplify out, and I just get the internals of that log all by itself. Notice what happened to that 2. That 2 became raised, or that 10 became that 2. That 10 had that 2 raised to its power there, and now I have 10 raised to the power of 2, and I get 100. Now these should look pretty familiar from Algebra 2, where I can distribute that x to both sides, and I get x squared plus 15x, and then I subtract that 10, or that 100 of both sides, and I get this polynomial function. Well, for that polynomial function, all I got to do is use that cross method to solve out, and I get x minus 5 times x plus 20. Now, look what happens with this solution here. I end up getting 2 solutions. X is equal to 5 and equal to negative 20. We need to double check and see if that negative 20 there actually does create a positive or a real answer for us. What I mean to say is when we double check these, we have this case here where we're taking the log of 5 plus log of 5 plus 15 is equal to 2. This is like a positive, which is fine. This is like a positive number, which is fine. But over here, we're trying to take the log of negative 20 plus the log of negative 20 plus 15, which really, it creates these non-real answers here. Now, this is a solution. This does equal positive 2, but it creates these i's, these complex answers here, which is not a real answer. These give us non-real answers, which we don't want in pre-calculus. We just want to focus on these real answers here. So we need to claim that the only answer here is x equals 5 because x minus 20 creates non-real answers. Let's put this into practice here, but instead of using logs, let's solve out these exponential functions. Now let's take a look at example 6 and example 7. In example 6 here, we want to try and solve out 8 raised to the power of x minus 3 is equal to 26. Now when I write this out, what I want to try and think about is, can I manipulate that 26 into the base of 8 here in any way? And I don't really think I can. 8 raised to the power of 2, like one of the smallest whole number exponents, would just be 64. So I don't really have a good way to make 26 into the same base as that exponential function there. However, I also know that if I made the log base 8 of both sides, that this log base 8 of this 8 raised to the power of x minus 3 is actually going to simplify out and just give me x minus 3 here. And all I'm saying is that this 26 is just taking the log of 8, or log of 8 there. I can just know that as some number, some decimal number. For the time being, I actually want to keep it as log of 8 of 26. I'm going to add 3 to both sides, and I end up getting x equals log of 8 of 26 plus 3. This here is an exact answer. An approximation would be me trying to make it into a decimal and then adding 3 to it. This here is an approximate answer, only because it has some string of decimal places here that I can't write. Now, I could write all of them as much as I can on a calculator, but it's still just going to be an approximation. This is the exact answer for my problem here. When I want to double check my answer here, if I plugged in 4.5668 into where x was up there, I end up getting 25.99928. If I try and add in a few more decimal places, like 4.566813 minus 3, I still only get up to 25.99987. Not exactly the 26 we want to try and go for with double checking our answers. However, if I use the answer, the ANS, instead of a calculator here, that keeps as many decimal places as I can in the calculator, I'll get 26. The reason for that is it's computing this here as accurately as it can into its calculations here. And it really is just trying to take that plus 3, that minus 3, simplifies it out, 8 to the power of log 8 of 26 there. It calculates log base 8 of 8. It just gives you that 26. So when you plug in that value into your exponent there, it does give you the exact answer. When you're writing these problems on the AP test, try and place this answer here. Don't worry about putting this answer unless it explicitly tells you to write down an approximate answer of 6, of 4, of 3 decimal places. If it asks for the approximate answer, give them the decimal places. If it asks for the answer, this is the answer. Log of 8 of 26 plus 3. Let's try this whole thing one more time in example 7. For example 7, we want to try and solve e raised to the power of x is equal to pi raised to the power of 1 plus x here. Now first, when I rewrite it, I want to try and think if I can manipulate these exponential functions to have the same base. I really can't manipulate pi to turn it into e or e and turn it into pi. So I need to use some logarithmic property of equality to get rid of one of those bases. I'm going to choose to get rid of that e first. If I use natural log with the base of e on both sides, it simplifies out that base e, so I'm just left with x on the left-hand side is equal to the natural log of pi of 1 plus x. Once I have this state here, look what I can do with this exponent. I can actually pull it out using that power property of logarithms there. Now initially, you might think that since we have this on the outside of the log, it really is just a product. So I could just say divide by 1 plus x on both sides, divide by 1 plus x on this side here, and I'm left with x divided by 1 plus x is equal to the natural log of pi here. But I don't really have a way to simplify out or get rid of that 1 inside of my denominator. So we're going to try and do something a little bit clever here. Take a look at this 1 plus x times log of pi. Really, if we use that property of the product, we can actually divide or like break up this log here into these two logs. And that 1 times log of pi really just is log of pi plus x of ln of pi here. Now I'm able to try and subtract this x of log of pi over to my left-hand side. And I'm given this x minus x of log times pi is equal to log of pi. Okay. Now that I have this set up here, I want to try and remove the x values from both of these terms here. I basically have this first term of x minus the second term with x times something else. Well, really, I can just pull an x out of both of those terms there. I'm going from x minus x log of pi into x times 1 minus log of pi. Notice what we're doing here. We're removing the x from both of those terms to get this here. All of our x's are now in one spot. They're isolated. And now I can divide away that 1 minus natural log of pi on both sides. When I do this here, the simplified out would look like this, where I'm just getting x by itself is equal to log of pi divided by 1 minus log of pi. This is just some decimal. What we really want to try and do in example 7 here is use these properties of exponents, these properties of logarithms, these properties of power, and these properties of product to try and get these x's by themselves. We end up getting to this sum decimal here, which is some approximation, where this here is the exact answer. And if we were to plug this in, we'd get the exact answer of x raised to the power of e is like negative 7.907 or 09 here. What we want to try and showcase is that when we're using these properties of equalities and exponents, you may go down some weird path where you can't just divide that 1 plus x to both sides. You might need to go down some weird path here to try and remove that x term from a log using those product properties from Algebra 1 and Algebra 2. Thank you very much for joining me on this second video for our Lesson 13A series. I look forward to seeing you guys in that final video. Take care.